Mesozoic. Geologic time scale, without spending 2 days on this, geologists have set up a time scale of the oldest rocks from the youngest rocks, and they're based on names given to them by the fossils that these particular rocks contain. The Paleozoic era is the big division in here. The Paleozoic, the Greek paleos meaning ancient, and zoic meaning life. This is the era of ancient life. The Mesozoic, Greek mesos meaning middle. So this is the era of middle life. And the Cenozoic, from the Greek kainos, is the era of recent life. So the age of the Earth is about 4.6 billion. The beginning of the Paleozoic is about 600 million. The boundary here between the Paleozoic and the Mesozoic is about 225. And then this boundary here between the Mesozoic and the Cenozoic is about 65. And that's an easy one to remember because how many of you have seen Jurassic Park? Dinosaurs became extinct 65 million years ago. So Jurassic Park started and ended in that particular area there. So the Sierra Nevada batholith is Mesozoic. We have Mesozoic granitic intrusions into these old seafloor things that are being plastered against the edge of the continent. Ages of these, this is from west to east, and these different cross hatches are ages of these different formations. If we start over here, the foothills right in here average about 0, 200, 150, 150 million years old. So in this particular area here, the foothills are right around 200 million years old, the rocks that we're sitting on top of right now. If you take a look at the crest of the Sierras up around Yosemite, the Tuolumne Meadows and area here are about 90 million years old. The older granitic and older igneous rocks are closest to the foothills. The youngest ones are on the crest of the Sierras. So they go from 200 million years up to about 80 million. And there are, as I say, as many as 18 or 19 different intrusive episodes of these kinds of rocks. This is a time scale with the different colors on it here, representing geologic ages. The batholith, mainly 125 million to 82 million. This is the age of the granite, depending upon what part of the Sierras you're at. These different colors in here represent that radioactive time dates. If you take a look at this, this is will be a little bit easier to see here and reference it to where we are. These are the radiometric ages, geologic time, of intrusive rocks in the central metamorphic belt. To give you an idea of where we are, this is the Pine Hill Intrusive Complex, this big mass of gabbro that forms Rescue, Cameron Park, this particular area here. That's the Pine Hill gabbro. Highway 50 actually runs right through this area here and goes on up in through. So this would be Highway 50. It cuts the southern end of the Pine Hill Intrusive gabbro. Right when you come off Bass Lake Road, you hit the top of the hill. Right at that top of the hill, you look and you see Bass Lake down to the right, or Marble Valley down to the right. That is the beginning, or the kind of the tail of the south end of the Pine Hill Intrusive Complex. If you look at this, this is then these stippled areas here. I'll just kind of draw that down there. Is part of the foothill fault system. This is the Bear Mountain fault system. The Bear Mountain fault system runs right up through Latrobe, through El Dorado Hills, and goes into Folsom Lake, right at Browns Ravine. So that's the Bear Mountain fault zone, a very, very rich gold and copper belt. And there's still a lot of gold and copper in that area there. I'll talk more about that a little later, about one of my students went down with a metal detector down there in Latrobe at the end of the semester. He used to go down there at lunch. At the end of the semester, he brought a briefcase in and set it on the table and pulled a mason jar full of gold nuggets out of there. He had 10 pounds of gold nuggets that he collected in a grassy field down around Latrobe, less than 18 inches beneath the surface, and wasn't a rock outcrop in the field. So keep your eyes open. You know, this class will change your ideas about driving around.
Had that been dredged, George?
Is what?
Had that been dredged? that area?
No. It's never, it's weathered rock, weathered about 18 inches deep, and the bedrock in there is a metavolcanic rock. Fort Gold. That's a good brand of bird bourbon. Susan's Gold.
That's gonna get interesting in about an hour.
This is Highway 50 through here. If you go up, this is Alvarado Hills, and you take a look at, let me get a lozenge and do both before I start coughing too bad. Bear Mountain's Fallen Zone goes through Alvarado Hills and runs into Lake Folsom at Browns Ravine, right there where you launch your boats. And then it runs into, and if you look at northern part of the lake, or the middle of the lake, you see these big, when the lake levels down, these big rounded outcrops of weathered granite. So granite was intruded into the old foothill terrain down in there and kind of obliterated the fault zone. So the intrusion of granite, this yellow area here is called the Penryn Pluton. And the Penryn Pluton is a massive granite. Auburn is located in here, Penryn is located here. So this is, Folsom Lake would be right around this particular zone here. So that shows you how long of that. In the mother lode, as you look at the geology and study it over time, you'll notice that the accreted terrains in these areas in here, the boundary between the different accreted terrains are the major faults. The Bear Mountains fault zone here, the central area here is the Maloney's fault zone, and then we have the east belt gold system in these particular areas in here. Associated in these old seafloor sediments, the gold was carried down. As groundwater percolates down through the ground and gets down to, if you have a large granite intrusion, a magma chamber coming up like that, you heat the groundwater, and the heated groundwater then percolates up through these old fractured sediments and rock, dissolving the gold and carrying it up, and then in the fault zones is the plumbing system of the gold veins. And the plumbing system, the rocks in the plumbing system, when we talk about the origin of gold, I'm kind of skipping around here a little bit because I'm giving you a preliminary introduction to the origin of gold that we're going to be going into next week. To concentrate gold in the Earth's crust and in the ocean basins in 2 or 3 parts per billion, average concentration. Pick up a driveway rock and it could have 2 or 3 parts per billion. To make a gold deposit or an ore deposit, the definition of ore, O-R-E, is something that can be mined for a profit. So you got an ore deposit, if you mine it and make money on it, you got an ore deposit. If not, it's really a neat group of minerals, and something that's really nice to look at, something like that. But ore is a monetary thing in that particular case. So what happens is and the gold scattered through these old accreted terrains is really low grade. But the hot water running through here and leaching it out in an acidic solution, to make an ore deposit, you got to concentrate that low grade gold in isolated areas and really enrich those. The ore deposits in the mother lode have been concentrated as much as 4,500 times the average composition of the Earth's crust. The concentrating mechanism is hot water running through these. So to get a gold deposit, you got to have, first of all, a source rock that contains the gold. The source rock would be the accreted terrains, part of the old ocean crust that came over the edge of the continent. You got to have then a fluid, an acidic solution that runs through that source rock and dissolves the gold and carries it in solution. So you have to have an acidic solution to dissolve the gold. And then as that acidic solution comes along, you have to have a host rock that has the kind of things in it that cause that acidic solution and the gold in there to precipitate out. So you've got a host rock, the seafloor volcanics, you've got the acidic solution that are part of the acid the ocean, solutions like that, and then hot water is mixed in, and then you have a host rock, and the host rock then is the rocks in these fault zones. And generally what happens is that you can dissolve gold in an acid or acidic environment. You can precipitate and concentrate gold in a reducing chemical environment. So as we go through and talk about the variety of different gold deposits, you'll see that the hard rock veins along these bare mountains and along this fault zone in the east areas in here, these are the kind of rocks that are reducing the environment chemically. So you dissolve the gold, you carry it in solution, and then run it into a reducing environment. Reducing. The graphite schist is a common accompaniment of gold quartz in the Maloney's Fault Zone. And so a lot of these hard rock mines, when you run across graphite, that's a natural reducing environment. That's what's going to collect the gold. The other kinds of things that will reduce it is that in the main central belt of the mother lode is the part of the sea floor where these ocean things were rafting across the Pacific were volcanic islands. And the volcanic islands had fringing reefs around them. And the fringing reefs then formed ultimately limestone. So you got a round car tire full of limestone surrounding these volcanic islands on that moving conveyor belt. That conveyor belt comes up, hits the continent, wrinkles up, tips up, and then is subducted down. Well, you subduct down the volcanic rocks, and then the tire of limestone around there is incorporated into the surrounding rocks. In the main mother lode, we have gold occurring with arsenopyrite, the iron arsenic sulfide. And arsenopyrite contains arsenic. But the main mother lode along that particular zone, the arsenic and the other sulfides don't form acid mine drainage because the limestone actually chemically buffers these things and the gold won't go into solution and it won't dissolve. So it's really kind of a neat thing is that the surrounding rocks next to the gold deposits are the things that stop it from going into solution. And we'll talk about that when we get into the hard rock mines and the chemistry of that.
What was the, George, could you repeat the phrase, an acid mine something?
Acid mine drainage. If you take a
So
look
that's
at
a reducing environment then?
okay, yes. Well, the acid mine drainage is our mines, particularly on what we call the western foothill belt, along the Bear Mountains Fault Zone, which is then Copperopolis,
Yeah.
and these other mines in there have a high percent of copper. Well, the copper mines have iron pyrite, FeS2, and they have chalcopyrite, which is CuFeS2, and then you have that purple iridescent bornite, the peacock ore, Cu5FeS4. When water reacts with these sulfides, it then forms sulfuric acid, and the sulfuric acid then naturally starts dissolving and it contaminates the groundwater. The Penn mine, which is on the edge of Lake Comanche, was a huge copper mine. When it was abandoned, it's full of water, and the water now is a natural source of acid mine drainage, just like the copper mines up around Chico and Redding in that particular area. So they continually keep putting acid and dissolving the bad metals in the solution. So the middle central part of the mother lode, the water is clean. It doesn't have the arsenic in solution. So it makes it very unique. And the chemistry of this is something that really needs to be, more attention needs to be paid to it.
So you're saying the calcium carbonate reacts with the sulfuric acid or whatever acid's flowing and then it neutralizes the acid?
Neutralizes the acid.
Okay.
There's a mineral called anchorite, which is an iron carbonate, FeCO3. And anchorite commonly occurs with the mariposite and the other in the Maloney's Fault Zone.
Makes sense.
So, the pyrite doesn't turn acid in that particular area. Well, what happens is that near these major fault zones, the Bear Mountains here, the Maloney's Fault Zone here, and then in the East Belt zones, near each of these major areas where you have an igneous intrusion of a granite or granitic type of rock up in there, that's a heat engine. And as that rock is intruded at a depth of 25 miles deep and starts to come up, groundwater percolating through the fractured rocks of these old terrains is going down. When it gets close to this heat engine, like a big furnace, it then turns to steam and hot water and starts migrating up through the plumbing system to the fault zones in these particular areas. So every time you have a major hard rock mine for 120 miles from Allegheny all the way to Mariposa, all these major mines have a nearby intrusive body of granite very close to it. The Penryn Pluton intruded in there, then caused mineralization along these fault zones there. So this is the granite, the age of that is about 165 million years old, the Penryn Pluton. The Pine Hill intrusive complex of the Gabbro is in this case about 166 million years old. You get down to Coloma, the yellow rock exposed in here